Okay, so hello. Okay, hello everyone. Welcome to Deep Learning Theory and Data Science. So first of all, I wanted to inquire about whether anyone tried to do the second coding exercise, and if anyone did try, if it's of reasonable difficulty.
I did it.
Okay, and
I found
how did you find it, Karen?
pretty simple. It took me 15 minutes.
Okay, thank you for the feedback. So at the very least, one person wants the homework to be a bit harder. Is that correct?
Yes.
Yes.
Make it harder.
Okay. So, okay. Neo wants me to remind everyone to like and subscribe and smash the like button and the notification. I figure out what the bell is. The bell is the notifications. So one student suggested in a previous lecture that I should also mention the bell. Okay, so here's the course website, and it was updated since the original launch of the website with this picture that was sent to me by a student in the course. And this is a picture of me saying empirical evidence has shown it is the best way to do it. I guess I did say that sentence many times in the first week or first couple of weeks. So I think this is a good image that represents the first 2 weeks of the lectures. So the first 2 weeks of the lectures were about an overview of deep learning. So basically basic terms, basic terminology of deep learning and so on. The second or the third week of the course was about mysteries in deep learning. And we discussed about information compression and sparsity a bit, the failure of theory, and about adversarial examples. And starting from this week, we're actually going to talk about what the topic of this course is, which is trying to understand better deep learning. Now, in each one of the topics, I will try to make the course as self-contained as possible. And so I'll present the background knowledge that is required to understand the topic. So for example, today we're going to talk about logistic regression, and I'm going to give an introduction to logistic regression. How many, are there people here who don't know logistic regression? Maybe I should ask. Oh, you don't know? Okay, that's great. Okay. Okay. So let's begin with logistic regression. So what is logistic regression? So logistic regression was proposed in the 1940s. And essentially it is a generative model. A generative model which is essentially saying that I have data X and I believe that the class or the label of Y, of the data X, is distributed Bernoulli with some probability P. So I believe that the label Y, given the data point X, is distributed Bernoulli with probability P. And essentially Bernoulli probability P means that the probability of Y being equal to 1 is P, and the probability of Y being equal to 0 is 1 minus B. Everyone remembers Bernoulli? Everyone likes Bernoulli? Okay. Now, this is the first assumption. The second assumption is that the probability of X is equal to 1 over 1 plus exponent of minus W inner product X. So that might look a bit strange to you. Why would we use such a function? But essentially what this function does is it takes the inner product of W with x, and it squashes it to the interval of 0 to 1. What does that mean? So imagine this is, let's use a different color. I feel like I'm using blue too much. So if this is W inner product X, right? And if you denote W inner product X by Z, then here you would have on the x-axis W inner product X. And on the y-axis, you can see the function 1 over 1 plus exponent minus W inner product X, right? And what you can see is that for very large W inner product X, this function is equal to 1 or tends to 1 because it becomes 1 over 1 plus exponent of essentially minus infinity, right? So exponent of minus infinity is 0. 1 over 1 plus 0 is 1. Does this make sense? So I guess a proper way to say it would be that as the inner product tends to infinity, this function tends to 1. This function tends to 1 as the inner product tends to infinity. Questions? Oh, what is W? Okay, so W and theta, so W and theta at this point are just equal to each other. Okay, it's the same thing. Why am I confusing you with two notations? You must ask yourself. Why am I confusing you with two notations? I'll explain that later. For now, I'm just an evil person trying to confuse you, but I do have a point. They're physically different. Yeah, they're a bit different. At the moment, let's just say they're the same, okay? So if W inner product X is very, very large, you agree that this function tends to 1, right? Do you agree? And if W inner product X is is tending to minus infinity, then this function is tending to 0, right? So that's why you can see this type of curve. When W inner product X tends to infinity, you get 1. When W inner product X tends to minus infinity, you get 0. And this function is called the sigmoid function, okay? So notice there's two assumptions here, two assumptions. The first assumption is that you have some probability P, which depends linearly on some W, right? That's one assumption. I guess it depends through a sigmoid and then linearly. And the second assumption is that the label Y given X is distributed Bernoulli with P. So let's do a very specific example, okay? My favorite example is cats and dogs. I like cats, I like dogs. Which one do I prefer more? Cannot say. So imagine that you're trying to classify images of cats versus images of dogs, right? In that case, the X would be an image of a cat or a dog, just an image. And the Y would be equal to 1 if it's a, let's say, dog, and 0 if it's a cat, right? And essentially what we're saying is that if I take an image of, let's say, a cat, and so let's say X cat, and I calculate an inner product with some W, and then I calculate the sigmoid of that, right? Then I would get, this is cat, this is dog. Then I would get something that's very small. Whereas if I had X a dog, an image of a dog, and I calculated an inner product with W and applied the sigmoid, I would get a quantity which is close to 1. Does this make sense? So perhaps this would make more sense. So imagine that, oh, equivalent to one layer network with sigmoid activation function. A logistic regression is equivalent to one layer network, and it is with sigmoid function. Yes, 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 yes. I'll actually make this connection extremely clear in the later part of the lecture. Okay. So imagine that we're in a setting where you care about classifying cats versus dogs, right? Oh, what does it mean to condition on X in this context? Is X a training vector and Y a test? Oh, so X is an image, and Y is the label of the image. So what does it mean to condition on X? It's basically saying that you have, it's a generative model, which means you're assuming something about your data. And what you're assuming is that there exists some W, right? That when you do an inner product with X and you apply a sigmoid function, you get a probability P, so that if you sample Bernoulli with this probability P, you get the label that you have. You get a label for the image. It's essentially an assumption about how the labels are being generated. We can also do this for multi-class. That's a good question, Gina. Thank you. So imagine we have a data set, okay, of cats and dogs, right? Just a bunch of images, cats, dogs, cats, dogs. Imagine that you're essentially like playing a god. You're essentially God, and you're trying to create the labels for all the images, right? How do you create the labels for all the images of the cats and the dogs? So under this generative model, what you do is you take each and every image X, right, which can be a cat or a dog, you do an inner product with W, you apply a sigmoid, and then you get a probability. And then you sample a random variable with the Bernoulli probability P. And that gives you a label. So it explains how do you assign a label to each image X. I feel like I'm repeating myself, but I'm not sure if I'm being clear on this point. Is it clear? If this is not clear, then you should definitely ask. Clear with an exclamation mark. Okay. It's just a very important point. That's not how God did it. Yeah. avoid such topics. So basically, this. Okay, so that's a very good question. So Jin Hui, hopefully I'm pronouncing correctly, Jin Hui is asking, will the label be 10% dog and 90% cat? Can anyone answer that question? What do you think? Because that shows true understanding of the logistic model, if one is able to answer this question. Under the logistic model, can you have an image which is 10% dog and 90% cat? So David says no. Kevin says yes. Maybe someone says maybe. Oh, and Amireza says maybe. So we have exhausted all possible answers. So Andrew says no. So we have a majority for no now. Does anyone want to say yes to equalize the number of? Okay. Yes. Okay, so we have majority of yes. So notice that. Jinhu, you see what you've done? You've created the confusion among all students. I'm actually joking. This is a beautiful question. Thank you for asking it. So under this generative model, notice that the process is as follows. You take X, which is an image, a fixed image, right? Let's say it's my cat. I have a cat. It's currently in Israel. This is the cat, okay? You see, cat. draw it. Okay, it's a horrible picture. So this is a cat. You take an inner product of this cat with W, and then you calculate P, which is equal to the sigmoid of W inner product X, and then you sample from a distribution of Bernoulli with probability P. Now, once you sample, what do you get? After you sample, you get a Y. So let's say you sampled Y equal to, in this case, 0, right? At this point, you have a pair of my cat, which is in Israel, and Y equal to 0. So in the, so to speak, data set, it's impossible for you to have an example of a cat, my cat in Israel, with a label which is, 90% cat, 10% dog. Does this make sense or no? I feel like it's less than clear. You got confused. Okay, let's do something simpler. Okay, let's do something simpler. Imagine you have a Bernoulli distribution. Imagine you have a Bernoulli distribution and you sample from the Bernoulli distribution, right? What are the possible outcomes? The possible outcomes are either 0 or 1, right? If you sample, like imagine you flip a coin. You flip a coin, it's either, head or tails. There is no, you cannot have a, it's not quantum physics. You don't have a both head and tails at the same time, right? Exactly. Neo put it beautifully. He said, so like you plug in the picture and get a probability P. Then you flip a biased coin with head probability P. If it is P, then you label cat. And if it is 1 minus, and otherwise you label dog. So it explains how God would have labeled the data set. So the person, Amireza, are you less confused now, or does this make sense, or more confused? Exactly. Yes. There is a chance that a cat picture will be labeled as a dog. It's just a very small chance. Do we do this to deal with vendors who label pictures poorly? So, okay, I want to remind you something. Logistic regression is a model from the 1940s, right? In the 1940s, there was no deep learning and so on. It's a generative model in the sense that it represents a person's belief about how data was generated. So for example, as Karen mentions, if you have a vendor that gives you pictures which are labeled poorly, then you might use a logistic regression model. And in the logistic regression model, your probabilities would be not very extreme, not close to 1 or 0. What does the W represent again? The W represents a linear predictor that multiplies your X to give you the probability P. It's good that we have a lecture on this. I was wondering, like, is this known, or don't think you understood that. So what W is? Okay, so imagine that you have a bunch of images. Okay, so in the case of classification, W is just the classifier. That's how you could refer to it. But it's essentially a vector that once you multiply by X and you apply the sigmoid function, you get a probability P. So it's a vector that's fixed, just a fixed vector. I have an idea. Let's do an example. Let's do an example. or no example. Maybe we should look at this example. Maybe that would clarify a bit things. So in this example, again, we have the cats and we have the dogs, right? Now, imagine I ask you, please classify cats versus dogs, right? And imagine that you do the simplest possible thing. What would be the simplest way of classifying dogs versus cats? What's the simplest possible way? If you remember, it's something that you learn in linear algebra. I guess it appears on the slide, so it's not a mystery, but linear regression on the left. So what does linear regression say? Line of best fit, exactly. So linear regression says the following. Take a data set of pairs xi and yi, right? And then define yi to be a vector. Let's say define yi to be either 0 or 1, cat or dog. And xi is, let's say, a vector corresponding to the ith example, which contains different attributes or features, right? You can think of it as the height, width, I don't know, color, whatever you want. And then what you do is you say, okay, I'm going to try and minimize the following thing. W, inner product with xi, I guess it's not even norm here, minus yi squared, sum over I, minimize over W, right? So you minimize the squared error and you get the line that best fits the data. This is called linear regression. Now, the issue with this is that if you're dealing with classification problems where the yi are either 0 or 1, notice what happens. So here you can see a bunch of examples, right, which correspond to different x data points, and all of them are being classified as 1, right? And here you can see a bunch of examples which are, you know, cases in which y is equal to 0. What's the difference between this plot and this equation, by the way? The difference is that in this equation, xi is just a vector in Rp, where p is whatever you want. Whereas here, in order to visualize, we just assume x is one-dimensional, right? So it's just, you know, weight, the weight of the animal, of the pet. So do you see how this is, in some sense, illogical? Like, why would you fit a curve, just a line to data that looks like this? It's just strange. So what logistic regression is saying is let's fit a curve which looks like this S letter, right? Why is that why logistic regression is doing? Because logistic regression is saying the following. It's saying that you take your x, right? You take your x, xi, and then you do inner product with w. After you do an inner product with w, you apply a sigmoid, and that gives you a number between 0 and 1, right? And what you want is that for that number to be either 0 or 1, depending on the example. Do I mean x? I mean, x and xi are related to one another. X is like an arbitrary input image, and xi is the ith example in a data set. X and xi live in the same space. They're the same thing. So x is like a general image of something, whereas xi is the ith image in a data set. So essentially what logistic regression is doing is it's, instead of trying to fit wxi to be yi, it's trying to make sigmoid of wxi to be equal to yi. That's the goal. And so what you can see here is that this is essentially here. You can think of this as wxi. And then here you can think of this as being the sigmoid value, right? And so do you see how this curve makes much more sense? So by applying the sigmoid, we get a fit which is much more natural. Okay. So are there any other questions about, the modeling assumption behind logistic regression? So this is logistic regression is a part of a more general family of algorithms, which are called GLM, generalized linear models. Why is it called generalized linear models? Because it's linear, right, in the W, but it's also generalized because you have this function that's applied on this linear part, right? That's why it's called generalized linear model. Extremely fundamental in statistics. Okay, so imagine that you have data, right? And your goal is to find the parameters of the model. What are the parameters of the logistic regression model? What are the parameters? W, exactly, yes. And Jinhui, that is correct. Logistic regression makes the distribution more polarized, which fits reality much better. That is correct, yes. So indeed, our parameter for logistic regression is the vector W. Now imagine I give you a set of training data, right? So a set of images xi and their corresponding labels yi. And I ask you, please find W. How would you do that? So the way you do it is by doing maximum likelihood estimation. What does maximum likelihood estimation mean? Something very simple. Imagine that I ask you, what is the probability of the data given the parameter theta? The probability of this whole data set given a parameter theta is just the multiplication of the probabilities of each individual example. Does anyone know why can we just multiply the individual probabilities? Independence, yes, exactly. Because they're independent, the probabilities are just the multiplications. Now, IID, yes. So it's both independent and identically distributed. Why is it identically distributed? Because the logistic regression, you're essentially assuming that all of these examples follow the logistic regression model. So they are identically distributed, right? Now, there is a trick that people like doing, which is instead of maximizing the multiplication of the probabilities, you apply minus log on this optimization. So the log function does not alter, if you maximize function or the log of the function is the same thing, right? Because at the end of the day, you care about the argmax, right? Or argmean. So if you do max of f of theta or max of log of f of theta, argmax, it's the same thing, right? Do you agree? Or don't agree? Because log is just monotonic, right? Now, moreover, instead of doing argmax, you can actually do argmean if you just apply a minus. So you get argmean log f of theta of minus the log, right? Now, why do people try to minimize the negative log likelihood instead of maximize this multiplication of probabilities? It is related to entropy, yes. But the way I'm presenting it is not through that. There's different ways to present it. I prefer to present it this way. Are they indeed IID? The distribution should be different for each x since the Bernoulli distribution is based off px theta. notice that the model only depends on W, right? So the only thing that I guess you could say that because they have different probabilities, they're not actually identically distributed. You could say that. But I guess notice that if you want to say that the probability of the data set is the multiplication of the probabilities, then you just need independence, yes. Exactly. For numerical reasons, it's much better to use log probabilities, because you don't want to be multiplying a bunch of probabilities, because that's very ill-conditioned. What does ill-conditioned mean? If you want to know, you should take a course in numerical analysis. So assume that we would like to minimize the negative log likelihood, right? Then one can show that the gradient of this L of theta here, which is minus sum of log probabilities, is actually equal to the sum of the probabilities minus the labels yi, which are either 0 or 1, multiplied by xi. So I decided to actually show you why that is correct, because I feel like at the very least we should derive one thing. So here's the claim. So what I'm going to show you is y is the gradient equal to the probabilities minus yi multiplied by xi. Before I do that, notice how beautiful this equation, this expression is. Why is this expression beautiful? Because notice that this quantity is just comparing the probability of the example to the ground truth label. So for example, if you would had let's say if you had yi equal to 1, you would want this probability to be equal to 1 for the gradient to be 0. And if yi is 0, you would want the probability to be 0. Does this make sense? So essentially, this is like, this is the label. So in some sense, it's like ground truth. And this is the estimated probability of being in the class, right? And so you want your estimated probability on this example to be equal to the ground truth label. Do you find this very intuitive and beautiful or no? Maybe we shouldn't carry it away with beautiful, but one could imagine much worse expressions. Okay. So maybe I should just solidify why is this beautiful. Notice that in this example, what is yi? Yi is, for example, this thing, right? This is yi, this thing. And what is the probability of xi? The probability of xi is this thing. And so if you're doing a subtraction between the two, you get this distance, right? And so this distance is very appealing because this distance is very similar to what you would get in a least squares case. In a least squares case, you would be interested in the deviations of this thing from this thing, right? So it's basically the same, you know, the intuition is the same. It's just a perturbation between your ground truth and your predictions. I mean, Reza is asking, it's a weighted sum in which weights are the errors. So those peaks for which there is no error won't be participating in computing the gradient. Exactly, yes, yes. Thank you, Reza. Yes, yes. So, yeah, so I would like to show how to calculate this gradient. So here's how it goes. There's actually a reason why I'm showing this. Later it would maybe become clear. So we're interested in calculating the derivative of the derivative with respect to W of the minus log probability of y equal to y given x equal to x, right? Now, the first thing I'm going to do is I'm going to show you a trick. The trick is, notice that the probability of y equal to 1 given x equal to x is equal to 1 over 1 plus exponent minus w inner product x, right? Notice also that the probability of y being equal to 0 given x equal to x is equal to the complement, so it's 1 minus this quantity, so it becomes exponent over minus w transpose x divided by 1 plus exponent minus w transpose x. And notice that this can be written as 1 over 1 plus exponent of w transpose x. Do you see this as being correct? So far, there's no magic. But notice, so what I did there was just multiply the numerator and denominator by the exponent of w transpose x. Now notice that you can write both of these equations, both of these equations in a concise manner by saying that the probability of y being equal to y is equal to the probability of y being equal to y given x equal to x is equal to 1 over 1 plus exponent of minus s w transpose x, where s is defined to be equal to so it's equal to 1 if y is equal to 1, and it's equal to 0 if y is equal to minus 1. Okay, so essentially you can write these two equations in a single equation just by introducing this s quantity. And s is just replacing your oh, sorry, I think I made a mistake. My bad, sorry. This should be 1 minus 1, and this should be 0. Does this make sense? So I'm replacing the labels of 1 and 0 with a sign which is either 1 or minus 1 in this equation. Does this make sense? Yeah. Now, why is this useful? Because we can plug this now into this equation and we get minus log probability. And then I'm just plugging this better way of representing the probability using this s. Okay. Now notice that you can write, so minus log probability of that thing is actually equal to the log, oh wait, I think yeah, so this PR is redundant, my bad. Yes, like this. So notice that the log of 1 over something is minus log, so you get log of 1 plus exponent minus SW transpose X. Okay, makes sense? Now, notice, I feel like I'm saying the word notice too many times. Notice that you can actually derive this quantity quite easily because the derivative, so the derivative of a log, So the derivative of a log is 1 over something. So you get 1 over 1 plus exponent minus SW transpose X, right? This is just the derivative of a log. Then the derivative of the inner pink thing is the exponent and then we need to derive the thing that's inside the exponent, right? And the derivative of the thing inside the exponent is minus x multiplied by s, which is the sign, right? Now, at this point, this thing is actually equal to 1 minus the probability of y being equal to y given x being equal to x. Is that correct? I think that's incorrect. It's equal to this minus 1. So let me move it here. Wow, this app is so good, Notability. And then this thing is multiplied by xs. Why is this correct? Because this quantity, because the probability of y given x is equal to this thing, right? And if you subtract this minus 1, you get 1 minus exponent divided by 1 plus exponent. Does this make sense? Or did you lose me? I can add a step if you want. I can also add no step if you don't want. So I'm not sure, is the thumbs up implying add step or no, don't add step?
I think we're good.
I'm good. You're good. Okay. Now, note, I should stop saying this. It's like my sister, whenever she writes proofs in math, she always keeps using, what does she say? Let us. Every sentence is let us. Maybe I should use let us to occasionally. So at this point, what I'm gonna do is, should I clear this? Let's divide into 2 cases. The first case is, imagine that you have s equal to 1. If s is equal to 1, then you get the probability of x theta minus 1 multiplied by x. Notice there is something a bit subtle here, that if y is equal to, if s is equal to 1, it implies that y is equal to 1 by the definition of s. And it also implies that the probability of y given, of y being equal to 1 given x equal to x is equal to the probability of x theta. Because the probability of x theta is this thing right here. Does this make sense? This part is basically equal to this thing if y is equal to 1. This thing is equal to this thing if y is equal to 1. Now, in the other case that we have is if s is equal to minus 1 and y is equal to 0, in that case, what you get is the probability of y being equal to y. So the probability of y being equal to 0 is 1 minus the probability of x theta. And then you get a minus 1 here because of the minus 1 multiplied by x multiplied by minus 1. And so overall, this becomes the probability of x theta multiplied by x. So if you combine this thing and this thing together, you get that the gradient is the probability of x theta minus y multiplied by x. Does anyone have any questions? Oh, magic, yeah. And this is the equation in the previous slide. So why am I wasting time deriving the gradients? The reason is that this way of defining the probability is actually pretty useful. And we'll be discussing a paper where this would be used and this would be used. So we need all of these definitions. Now, this was a proof or an attempt of a proof for why the gradient of the loss is equal to the probability minus the one hot vector multiplied by x, right? Does this make sense? But notice that here we have a sum because we have a bunch of examples, right? So we have a bunch of examples. For each example, we have a gradient. Give me just 1 second. I'll turn off my heater. Otherwise, it would make a lot of noise. Okay, I'll sit in the cold. Sacrifice my warmness for the lecture. So this is the gradient. Now, another quantity that is of interest usually is the Hessian. So the Hessian is the second derivative of your negative log likelihood, which is essentially the loss with respect to the parameters theta. So I should add here theta, right? Now, I'm not going to derive the Hessian, but the Hessian is equal to the sum over the examples of P, which is this sigmoid probability, multiplied by 1 minus P, multiplied by XX transpose. Okay. Now, at this point, what is the first question people ask themselves when they look at optimization problems? I guess these days there's no questions. You just use gradient descent. Is it okay? Tristan knows old school optimization before we just converged to using gradient descent everywhere. So this is indeed the question. Is this problem convex? So does anyone know if this problem is convex or not? Tristan does not think so. Oh, maybe I should first ask, does everyone know what a convex problem is? Kind of. I feel like there's a kind of okay, so intuitively speaking, okay, I didn't prepare my definition of convexity. So this is from the top of my head, but a convex function intuitively is a function where at each point in space, the Hessian is positive definite. That's one definition. So if the function looks like, I guess, this. So if you can prove that this is positive definite or positive semi-definite, that means the function is convex. So usually the way people explain what a convex function is through a drawing. Imagine if you have something like this, and okay, this is a horrible drawing. Okay, let me do an example of a non-convex. This is a non-convex function. A function is convex if every 2 points that you choose and that you connect with the line is below the function, is above the function. So if the line is always above the function, it means that the function is convex. In this case, it is not convex. So what would be an example of a convex function? So this would be a convex function. Because every 2 points I choose, if I connect them with the line is above the function. Does this make sense? So this is one definition of convexity, but there is a bunch of equivalent ways to define convexity. One of the ways to check for convexity is to check if the Hessian, the second derivative, is positive definite. I guess I should also ask if everyone knows what positive definite is. So I'm assuming things. Please feel free to ask anything, you know. So positive definite is a matrix whose eigenvalues are all positive, right? Okay, so let's see, what did I miss? Okay, so hopefully we know what convexity is. Andrew says he believes it is a convex problem. Alik says it's convex. And Mireza says it's not. Andrew says the convexity is. Okay, so how do we know that this function is convex? So basically, or not convex, basically, because P is less than 1, as Gina says, then these quantities are always positive, right? These quantities are always positive. And essentially, the Hessian is a sum of some positive weights, let's call them maybe Wi is bad, alpha I, xi transpose. And one way of checking whether a matrix is positive definite is by sandwiching it by a vector from the left and from the right, right? And here you can clearly see that this thing is always positive. Do you consider P as a constant or a function of X? It is a function of X. It is a function of X. But how is this related to the question of convexity, Amireza? Or is this just a question in general? Oh, I just gave a different notation. It's like define P alpha I to be P1 minus P. I guess a proper way to do it would have been to do alpha I of X. Yeah, so I define things on the left and on the right without specifying what it's function of. This is a sloppy definitions. I'm sorry for the sloppiness. No, you're correct. You're correct. I just, okay. So everyone agrees that the Hessian is positive definite and that this problem is convex, right? Now, the next question you might ask yourself is, how do we find the parameters theta, which I remind you are equal to W? So the first thing you might say is, let's use the one algorithm that we like and that solves all our problems, which is known as gradient descent, right? But logistic regression has been used, I remind you, since the 1940s, right? And back in the days, people used to do more fancy optimization algorithms. One example of a fancy optimization algorithm is called Newton's method. What is Newton methods? Newton methods is an optimization algorithm that uses both the gradient and the Hessian to optimize a function. So the way it works is as follows. You take your parameters at the current iteration, theta t, you calculate the gradient with respect to the loss, right? And then you multiply the gradient by the inverse of the Hessian. Okay? So it's just the only difference between this and gradient descent, which we love and cherish, is that here we have the inverse Hessian. Now, why would you use the inverse Hessian? There's, theorems in optimization theory that explain why the rate of convergence is significantly faster if you use the inverse Hessian and the Newton method. Essentially, you can think of this as just applying some type of a transformation on your optimization algorithm that makes it more well conditioned. So essentially, if you have a imagine you have a optimization algorithm where your level sets look like this, right? So it's bad level sets. If you use the Hessian, the level sets would become more isotropic. This is like intuition in one sentence for the Newton method. If this doesn't make sense to you and you would like to learn more about this, you should, I guess, take an optimization course where you would learn about this more properly. Does the inverse Hessian thing only work for convex problems? Is it more a general thing? It's a beautiful question. You can use the inverse Hessian thing for non-convex optimization, and people have been using it in deep learning, for example, but it's not as popular, and it's a very lengthy discussion. Essentially, there's certain phenomenon that happen in non-convex high-dimensional optimization when you use this second-order optimization, which are non-trivial. So I would prefer not to talk about them at this point. But if you ask me at the end of the lecture, I'd be happy to explain what I mean by that. So I guess the answer to your question is that, yes, you can use it for non-convex optimization. Luke asks, is the Hessian always invertible? Is the Hessian always invertible? So for example, if you had two examples which were the same, two x's which are the same, then the Hessian would not be invertible, right? But if your examples are always all different, then the Hessian, would it always be invertible or not? I guess in practice, yeah, you need a spanning set, but I think in practice, practically speaking, these examples xi, essentially the Hessian is a sum of n rank 1 matrices. In practice, if n is very, very large, let's say, I don't know, 1,000, and the dimension of the examples is small, let's say 10, then you will always have a positive definite Hessian. That's like answer number one. Answer number two is that you can always add some type of a regularization term to the optimization, something like lambda multiplied by, you know, your vector of parameters squared, which we called weight decay in previous lectures. And that would create a plus lambda identity in the Hessian, which would make it always positive definite. You need enough linearly independent xi for this Hessian to be invertible, right? Yes, 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 yes. Okay, so there is actually a very nice interpretation of this Newton's method in the context of logistic regression. And the Newton method that I'm showing you here is something way more general, right? You can use Newton method for, you know, basically whatever optimization problem you have, right? It's not specific to logistic regression. But if you use it specifically for logistic regression, it has a beautiful interpretation. And let me try to explain what that is. So notice that the gradient is equal to the sum of p minus yi multiplied by xi. So how do we know that? Based on our small derivation, right? So our derivation calculated the gradient of the loss with respect to theta. Notice that the gradient can be written as x multiplied by p minus y, where x is a matrix of size p times n. P is the dimension of an example xi, and n is the number of examples. So maybe I should define these things properly. So P is a vector of probabilities in Rn, P at place I is equal to the probability of xi theta. Yi is a labels vector. So yi is in the set 0, 1. And X is just a matrix which contains in its columns the different xi's. Does this make sense? Now, why do we want to write the gradient as x times p minus y? Because this is very intuitive in some sense. Why is it intuitive? Because it's saying that the gradient is a linear combination of our examples x, right? Because it can be written as a matrix multiplied by a vector. So the gradient is a linear combination of our examples xi, and also the weights that are in this linear combination are these deviations of the probabilities from the one-hots. So I think Emireza, was it Emireza who said this earlier? Let's see. Yes. So if you look at Amireza's statement beforehand, she said it's a weighted sum in which weights are the errors. So that was said about the gradient. It's a weighted sum in which the weights are the errors. So these are the gradient, this is the gradient, is a weighted sum of xi in which the weights are the errors. So compactly, it's just x multiplied by p minus y. Now, moreover, the Hessian matrix, which is the second derivative, can be written as x multiplied by d multiplied by x transpose. Why? Because, when D is a diagonal matrix which has at the II location P multiplied by 1 minus P. So why is this equality correct? Is it clear for everyone? Why is this correct or not clear? So one way to see it is that if you have x multiplied by d, if you just restrict your attention to this multiplication, what does multiplying x by a diagonal matrix do? It's just scaling the columns, right? It scales the columns of x by those entries. So x times d can be interpreted as being this quantity, right? X is scaled by something. And then once you multiply it by x transpose, you get, the outer product of the columns in xd with the rows in x transpose. Now, why is any of this interesting or useful? Because notice that our update is theta t plus 1 is equal to theta t minus the inverse of the Hessian multiplied by the gradient, right? Notice that we can just plug in, instead of the gradient, we can plug in x times p minus y, right? That's what I'm doing here. And notice that instead of the Hessian, I can plug x dt x transpose. Does anyone have any guess why am I using pt here? What does pt mean? What is the definition of pt? The tth iteration. So it's the probability, it's the vector of the probabilities of the tth iteration, right? And as Karen says, the probabilities depend on theta and theta depends on time. So the probabilities depend on time. Now, the same argument explains why we have dt here. dt is a diagonal matrix of probabilities, and the probabilities depend on time, right? So the matrix D depends on time. So next, notice that we can massage this expression, we can massage it and write it as x dt x transpose inverse times x dt x theta t plus d inverse y minus pt. because, let's see, if you multiply this whole thing by that thing, you get theta t. And if you multiply this whole thing by that thing, you get, I guess, this thing, right? Why is this useful? This is a very strange derivation, right? This is useful. No, imagine if we denote this by zt, right? Just give it a name. This is zt. What is this expression here? Does this expression mean anything to you? Backprop? No, it's not backprop. So it's a very fast answer also. But no, it's not backprop. Does this look like something that you've seen in your life? An orthogonal projection. Not quite. It's close to an orthogonal projection, but not quite. Not quite. So maybe I should spoiler this. So this is least squares, exactly, Kevin. Yes, yes. This is least squares. So this is the thing we had in the previous slide. Notice that this quantity is the solution to this optimization problem, which is almost least squares. So let me remind you least squares in 2 slides in case you forgot. Least squares says if you have x theta minus z, and then you have, let's see, 2 squared, right? Is this what we have? I guess we have x transpose. So this, imagine you're trying to minimize this with respect to theta. Do you agree this is a least squares problem? Yes, because yeah. So the minimization is going to be, if you write the optimality condition, you get, what do you get? You get x multiplied by x transpose theta minus z equal to 0. And then you get x transpose theta is equal to x z. And then if you, oops, let me rearrange. If you multiply by x transpose on the left, you get x transpose xz, right? So compare and contrast this thing with this thing. Do you see how they almost look the same? Why almost? Because we are missing, because in this expression, you also have this dt, right? So why do we have here a dt? Because instead of doing the regular least squares, we're actually doing here a least squares where you multiply here by a diagonal matrix of some sort. So it's essentially equivalent to, you know how in least squares, you're essentially penalizing deviations, right? Using an L2 norm squared. If you have here some diagonal matrix, it's essentially saying some directions are more important than other directions. Does this make sense? It does make sense. Yes. So to summarize, what we've done was we started with a logistic regression problem. After the logistic regression problem, we proposed an optimization algorithm, which is called the Newton method. And this Newton method, we showed that it's equivalent to doing something that is very similar to a least squares problem, right? Now, notice that in this expression, maybe I should add an extra step here. Is it clear to everyone that if I add here a certain dt minus half, right? And I redo the calculation, then is it clear to people what would happen? Or it's not clear? Should I do this? I feel like I should do this. Okay, let me just rewrite this thing so it makes sense. So this is a least squares problem where I inserted this diagonal matrix dt to minus half, right? If I just derive this with respect to theta, what do I get? I get x multiplied by dt minus half, right? Multiplied by dt minus half multiplied by x theta minus z equal to 0. This is just the optimality condition of this optimization problem, right? Which is obtained by deriving with respect to theta. And then notice that this is equal to x dt. I think I messed up something. X dt multiplied by x transpose theta is equal to x dt multiplied by z. I think I messed up something. Just give me 1 second, please. I think this thing should be a half, not a minus half. So let me just remove the minus there. It's a small mistake. So then what you end up having is theta is equal to x dt x transpose inverse x dt z. Does it make sense now? It does make sense. So why is this algorithm called iteratively reweighted least squares algorithm? So let's decompress this very long name, which is shortened by IRLS. First of all, why do the words least squares appear in the name? Because we're doing something that's similar to a least squares problem, right? Why does the word reweighted appear in the name? What's being reweighted here? The fact that you're using this d to the half implies that you're essentially reweighting your least squares problem, right? Reweighting in the sense that certain directions are worth more than other directions in the objective. I'm not sure, is it clear the concept of reweighting? I'm getting kind of a mixed gazes. I'm not sure. Some of the gazes seem like they understand what reweighting is, and some, it is clear? Okay. And then the last word is iteratively. Why is this iteratively? Why does this iteratively word appear in the name of this algorithm? Why do you have to iteratively solve this algorithm? The t plus 1, yeah, so that's the correct answer, but exactly, dt is not constant, right? So your dt is a diagonal matrix that depends on the probabilities, and the probabilities are dependent on time, right? So dt depends on time, so you need to iterate this least squares problem. So hopefully the name makes sense now, and we can proceed. Okay, so next thing, at some point, I think Gina maybe asked, is this logistic regression capable of handling many classes, right? So there's something called multinomial logistic regression. Multinomial logistic regression. Multinomial is a fancy word for saying multi-class. I guess statisticians like this word better. In the case of multinomial logistic regression, you have something very similar. In binary class, in the regular logistic regression case, we had that y given x was Bernoulli with probability p. What's the generalization of Bernoulli to multiple outcomes? The generalization of Bernoulli to multiple outcomes is called the categorial distribution. Categorial. Now, in the case of a categorial distribution, what is P? What is P? What is this P? Is this a scalar? Is this a vector? Is this a matrix? Is it a function? Is it a tensor? Is it a, I ran out of ideas. What is P? should be a vector, yes. And what is the length of this vector? Yeah, exactly, vector, and it's the probability for each category. That is correct. Number of classes is correct. So essentially, P is a vector of length number of classes. And let's do an example, P equal to 0.5, 0.3, and 0.2. So now, in addition to the cat and the dog, we need a third class, which is our third favorite pet. What is our third favorite pet? A turtle. What? Strange. Turtle. I don't know. I guess fish was the answer. They live a long time. That's actually a good. That's actually a good reason to get a turtle. A roommate. That's interesting. Yeah. Hippo. Yes, I think hippos are costly. You know, the only person who could ever afford hippo pets was, I guess, Pablo Escobar. So essentially, we have a generative model which is assuming that our labels are coming from a categorical distribution with a vector P. And so what does it mean to sample from a categorical distribution with vector P? It means that with probability, let's say half, I'm going to have a one-hot vector corresponding to a cat. With probability 0.3, I'm going to sample a one-hot vector corresponding to a dog. And with probability 0.2, I'm going to get a turtle, right? Now, in this case, if you remember in the logistic regression case, we had to specify that the probability is equal to a sigmoid of W transpose X, right? And in that case, the probability was a scalar between 0 and 1. In the multinomial logistic regression case, you need to do a generalization. So how do you create a generalization of the sigmoid W transpose X? So one thing you might want to do is, instead of having W transpose X produce a scalar, now you want W transpose X to create a vector, right? A vector. What kind of what is the vector? The vector is in RC, the number of classes, which in this case is 3. Now, I guess it's horrible for me to use the same notation for the vector W and the matrix W, but I hope you will forgive me. And the second thing you might want to do is you might want to take this W multiplied by X, and you might want to apply some function on it that would make it a probability, right? What kind of function might you want to apply? So in the case of multinomial logistic regression, this is the function that you apply. This is the function. So let's try to understand what's happening here. You take an input X, which is an image of a cat or a dog or a turtle, and then you compute an inner product with WC. Afterward, you apply an exponent, and you normalize this by the sum of all the exponents for all the WC primes, right? So if in the previous case of logistic regression, W can be thought of as a classifier, in this case, WC prime can be thought of as, does anyone have any guess? What is WC? What is WC? I guess the answer is, yeah, exactly. WC is like the vector W, but for the class C. And it's not the column C of matrix W, it's actually the row, but that's also correct, yes. It's the Cth row of W. I guess one thing maybe that's unclear to, I don't know, maybe you can tell me if it's clear. Is it clear to you why can W in the previous example be thought of as a classifier? Is that clear or not clear? It is clear. Okay. So in this case, WC is the classifier of the Cth class, as Kevin said. Now notice that this thing is equivalent to the softmax function that you might remember from lecture number 1 or 2 or 3. So what does this mean? What does this mean? It means that in this case, we have a different generative model that applies for multi-class classification. In the case of binary classification, we had only one vector W, but now we have CW vectors. Can we conclude the matrix of matrix W is at most n minus 1? C minus 1. So it's actually a good question because it touches on I think a big, how should I put it? What you're saying is correct, Amireza, but essentially there is a difference between what people in statistics do and what people in deep learning do. In statistics, people apply linear algebra to the problem and they say, okay, it only makes sense to have C minus 1 classifiers. Because if you're trying to, classify C classes, if you make C minus 1 decisions, the last decision is useless. You don't need the last classifier. So it is correct what you're saying, Amireza, but in deep learning, people actually train a classifier of C classes, not C minus 1. And I can explain at the end of the lecture why that is, but I don't want to confuse people because this is kind of a touchy point that I'm not sure is worth confusing people over. So similar to how we calculated the gradient and the Hessian and the Newton method and the RLS algorithm for the binary classification case, you can also do the same thing for the multinomial multi-class case. So in this case, we have examples xi, which are either an image of a cat, dog, or a turtle, which lives long, and yi, which are one-hot vectors, right? So it's a vector of length 3 with one at a certain location. Now, in this case, you can also define the negative log likelihood, which has the same shape. But notice that there is this theta here, right? Does anyone have a guess for what is theta now? What is theta? What is theta? Yeah, theta is the vectorization of W. So theta is a long vector that contains first the classifier of class, I guess I should make it longer, W1, then the classifier of W2, then the classifier of W3, and so on. Okay. So theta is the vector of parameters which contains all the different classifiers. And you might wonder to yourself, what is the gradient in this case? What is the derivative of the negative log likelihood, which is basically the loss, with respect to theta? And the gradient is equal to something. Okay, let me start with a simple description of what the gradient is before I confuse you completely. So the gradient of the loss, let me write it this way. The derivative of the loss with respect to the W matrix is equal to sum over P xi theta minus yi multiplied by xi transpose. Let me put it here. So let's oops, let's go term after term and verify we understand each other. So the derivative of the loss with respect to W, what would be the dimension of the derivative of the loss with respect to W? Would it be a scalar? Would it be a vector? Would it be a matrix? Would it be a tensor? Would it be a function? Would it be a turtle? So I saw a single node for the word matrix, and that is correct. If you're deriving a scalar with respect to a matrix, you get a matrix, right? Now, here we have a sum of I from 1 to n of pxi theta. So what's pxi theta? Where is it living at? Pxi theta is a vector in Rc, the number of classes, right? Yi is also a vector in Rc. So if we subtract both, we get the difference between our estimated probabilities, between the softmax probabilities and the ground truth label. Do these words make sense? Does this seem to you like an intuitive quantity? It's analogous to what we saw in the previous, in the binary case. I was trying to emphasize how you have these, you know, oh, okay, horrible plot. Okay, there is no way I can plot this properly, but there was this, you know, point on the line on the S curve, and then there was this point, and I was emphasizing that the difference between the two was in the gradient, right? So here you have the same thing, except the difference is between two vectors. One is the one hot vector, and one is the vector of softmax probabilities, okay? Now, notice that the gradient that I wrote here is a bit different. It's written a bit strangely, perhaps. The reason is that what I'm writing here is the gradient with respect to theta. The gradient with respect to theta is the derivative of the loss with respect to a vector. What is the derivative of the loss with respect to a vector? It is a vector, right? So we expect here to get a derivative which is a vector. So essentially what we want to do is we want to take this derivative and we want to vectorize it. So how does one vectorize an outer product of two vectors? How does one do that? Tensors, yes. So let me introduce something which is called a Kronecker product. Kronecker product is essentially a cousin of the tensor product, but it's a more friendly, it's a friendly cousin, okay? So what's the difference between Kronecker products and tensors? Essentially, the difference between Kronecker product and tensor product is that same difference between matrices and linear operators. So I'll leave it at that, the difference. But let me explain to you properly what is a Kronecker product. So a Kronecker product takes two matrices or vectors or scalars, whatever you have, and it just constructs a matrix where you take B and each time you multiply by a different entry in A. So first you do A11. Oh, I should ask, how many people here, is there anyone who doesn't know Kronecker product? Because maybe I'm wasting my time. Okay, I don't waste time explaining things which are known. So essentially you take B, right? And you put it in all the different locations multiplied by different entries from A. So first it's A11, then A12, A1n, A21, A22, A2n, all the way to AMN-B, right? So if A was a matrix that was this size and B is a matrix that is this size, what would be the size of A Kronecker B? It would be, I guess I should make it to scale, something like this, right? Huge. Because essentially you're repeating this B many times, right? Does this make sense? The dimensions? Maybe this is a horrible way of explaining what this is, but hopefully the equation hopefully is a good way of explaining. This makes sense, right? Now, why do we care? Oh, okay. So when does Kronecker product arise in our everyday life? When does it arise? It arises when you're trying to do differentiation of, for example, if you're trying to differentiate a vector with respect to a matrix. So what is the derivative of a vector with respect to a matrix? It's a tensor, right? Because, yeah. So essentially, instead of doing dv to dw and then getting confused, what you do is you do dv to d vec of w, where vec of w is the vectorization of w. And this naturally leads to Kronecker products. So I don't want to confuse you too much at this point, but just what's important to understand is the definition of the Kronecker product. And also that the Kronecker product has a bunch of very useful properties. What kind of properties? So one property is bilinearity, which is written here. So A Kronecker B plus C is equal to A Kronecker B plus A Kronecker C. Very intuitive property, right? So essentially, okay, the second property is B plus C Kronecker A is B Kronecker A plus C Kronecker A. Also very intuitive. The third property is if you multiply A by a scalar, it's equivalent to multiplying B by a scalar, or it's equivalent to multiplying the Kronecker product by a scalar. Also very intuitive. Something that's perhaps a bit less clear, I would say, is that the Kronecker product of AB, if you Kronecker it with C, it's equivalent to Kroneckering A with B Kronecker C. It's less intuitive, right? Less intuitive. And perhaps the least intuitive property, but perhaps the most useful property, is that A Kronecker B matrix multiplied by C Kronecker D is equal to AC Kroneckered by BD, where here you have matrix multiplication. Does this make sense? So just think of the Kronecker product at this point as a new operator which has certain possibly cool properties. Okay. Now, why are we talking about Kronecker products? Because imagine that you have an outer product, trying to decide where to explain this. Imagine you have an outer product of A and B, right? A, B transpose. How can you write it using Kronecker products? How can you, so imagine you have AB transpose. What is AB transpose? It's a matrix, right? But imagine you would like to write this matrix in a vectorized form. So you want to write the vectorization of AB transpose, which would be a vector. What is vec AB transpose equal to? You know, I showed you properties of Kronecker product, but I haven't shown you the single property that you actually need in the previous slide, which is my bad. So it's actually equal to, so Xiaoding says it's B, A tensor B, but it's actually B tensor A. But close enough. So why is this correct? Why is this correct? Let's begin with intuition. If you have an outer product of two vectors, right? Then essentially what you do is you pick an entry from the first vector, multiply it by an entry from the second, right? So notice that in the definition of the Kronecker product, you get, what would happen if you do the Kronecker product of two vectors? Essentially, each entry in the first vector would meet each entry in the second vector, right? Or wrong. Maybe I can do an example. Imagine you have A11, A12, A13, Kronecker product with B11. Oh, I don't even need the one. Let's do it simpler. Imagine you have A1, A2, A3, Kronecker product with, let's say B1, B2, B3, B4, right? What does that give us? It gives us A1, B1, A1, B2, A1, B3, A1, B4, A2, B1, A2, B2, da, 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 da. Ran out of space, right? Now, notice, if you calculate the outer product of AB transpose, what do you get? You get A1, A2, A3, outer product with B transpose, which is B1, B2, B3, B4, right? What would that give us? Let's make this smaller. That would give us A1, B1, A1, B2, A1, B3, A1, B4, A2, B1, A2, B2, A2, B3, A2, B4, da, 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 right? Do you see how up to rearranging of terms, these two quantities are the same, right? Do you see that? Is it clear? So essentially, what is the difference between the outer product of two vectors and the Kronecker product of two vectors? What's the difference? The difference is that the outer product of two vectors is a matrix, whereas the Kronecker product of two vectors is just a longer vector. And what is the relation between the two? What is the relation between the two? The VEC operator, because VEC of the outer product, so if you look at this thing, the VEC of the outer product is equal to B Kronecker A. You can relate the outer product with the Kronecker product. So let me just write one property which I forgot to write in the slide, and it's probably the most important property. The most important property is that VEC of A multiplied by B, where A and B are either matrices or vectors, but they should align in terms of the dimensions, is equal to B transpose Kronecker an identity multiplied by the VEC of A, and is also equal to I Kronecker A multiplied by VEC of B. So this is just a property that you can prove for Kronecker vectors. And why is this useful? Because this equation is due to this property. Do you see that this is due to this property? Or did I get the incorrect property? It seems like I got an incorrect property. One second. Let's see. VEC A, VEC B. Yeah, I think I got the incorrect property. Okay, there is incorrect property. This is the incorrect property. There is another property that you can use just to prove this this thing immediately, but I don't have it at the top of my head. So if we go back to the previous slide, right? In the previous slide, we had a gradient of the loss with respect to the weights. And so this gradient is equal to a matrix, right? It's a matrix. We ignore the VEC property. Yeah, just ignore that thing. Ignore that thing for a moment. There is a way to prove this, which is, I guess you can prove this just by, looking at this and looking at this, right? Just by inspection, you can see. But there is a very easy way to prove this using a property that I forgot, unfortunately. I mean, you can prove it just by definition of VEC and the definition of the Kronecker. if you want. Okay, so in the previous slide, we had the gradient of the loss with respect to the weight matrix, right? And we said that this thing is a matrix. Notice that this thing, we also said, is the sum of these outer products. Now that you've learned about the Kronecker product, don't you have an urge to take this outer product and turn it into a Kronecker product, right? Do you have such an urge? You do. It's possible I got here the order incorrectly. It's very common to make this mistake. Yes, it is very possible. So at this point, you understand what is the Kronecker, and you understand how the gradient here can be written as function of the Kronecker. Notice that, as I mentioned previously, this is the gradient of the loss with respect to a vector theta, right? So we would expect this quantity to be a very long vector. And indeed, this is a long vector. Does this make sense? Now, in addition, you might be interested in the Hessian of multinomial logistic regression. The Hessian of multinomial logistic regression is also, I like the reaction of Andrew, is also, you can also write it with a Kronecker product. So let me give you a motivation for a Kronecker product that you would not be able to deny, refute. What is the Hessian? The Hessian is the second derivative of a loss with respect to the parameters W, right? So if you think about it, W is a matrix. If you derive the loss, which is a scalar, with respect to a matrix twice, what do you get? What does this lead to? It leads to tears, right? Because this is a 4D tensor, 4D tensor. And we don't like 4D tensors, do we? So instead of looking at the second derivative of the loss with respect to W, what you do is you look at the second derivative of the loss with respect to the vectorization of W, which is theta, right? And this leads to a 2D tensor, which is actually a matrix, right? And this transition from W to theta, which is the vec of W, is essentially the transition, is essentially what's causing this Kronecker product here to appear, right? Because here, essentially, we have, the derivative with respect to the vec of W squared, right? Because of this vec, you get a Kronecker product here. I mean, a different approach could be just try to derive that the Hessian is equal, what is the Hessian equal to? Just write down, the derivative of the loss with respect to the theta, and then do it again. And you would see that it leads to this equation. I just don't want to do that because it would be, unfortunately, quite painful. So notice that once we have the gradient and we have the Hessian, we can actually do Newton's method, which is again the same type of optimization method, right? And this Newton method can also be shown to be equivalent to an IRLS algorithm, but I'm not going to show the equivalence. So hopefully what we've learned today is about the logistic regression model and the multinomial logistic regression model. And I emphasize again that this is a key word, generative models. Generative models means that it represents your belief of how are labels generated for your data, right? And we saw that we can fit the model. And it's important to emphasize also that you can fit the logistic regression model to data even if the data does not satisfy your assumption. When you run an algorithm, it doesn't mean that you believe that the assumptions of the generative model make sense. You can just run an algorithm on data. Do you see this distinction? There is a distinction between an algorithm and a generative model. The generative model is saying that I believe that y given x is, let's say, Bernoulli with a probability p, right? But the fact that you run an algorithm on a bunch of cats and dogs does not mean that this assumption has to be correct. You can just run the algorithm, right? So this is the difference between the generative model assumptions and the algorithm that they lead to. The algorithm can always be applied no matter whether the assumptions hold. So this is the end of the lecture. I'm sorry I went over by 6 minutes, and I'll remain for questions. Thank you for joining today as well. Why do they call it generative models? Because they generate, in this case, they generate the labels, right? So I think that the word generative model should be contrasted with discriminative models. Discriminative models are models that only care about, no, it's not about the P, no. A simple example of a generative model is, for example, the Gaussian distribution. The Gaussian distribution explains to you how data is, constructed, so to speak, right? What is the Gaussian distribution? The Gaussian distribution is a function which says that with a certain probability, you sample a certain example. So it's a generative model. It generates data. The logistic distribution is also a generative model because it explains how to generate the labels for your data. What is not a generative model? That's a good question. So a deep network is not a generative model, the classical deep networks like the multi-layer perceptron, because essentially what it's doing is it's trying to predict y given x, but it does not specify how to generate the labels, right? I guess certain people do interpret them as generative models, but in deep learning, a generative model would be, for example, GAN. Have you heard about GANs? In some sense, it's a generative model, I guess. It's not, you heard. What would be a non-generative model? Let me think. For example, nearest neighbor, SVM, exactly, SVM, support vector machine, is not a generative model because it does not explain how is data generated. Karen, your background colors are becoming more and more beautiful. It's just amazing.
It's just my camera's worse today.
Oh, okay.
Actually, I have a question.
Mm-hmm.
If we generalize beyond just Bernoulli
Mm-hmm.
categorical distributions, do we have analogous algorithms that turn out nice?
Algorithms that turn out nice. I think there are, but I'm not very aware. I think it's a question you should ask a seasoned statistician. This would be the person to ask. I guess one thing you could imagine is, what would be a generalization? I think one generalization, there's something called generalized linear models, GLM. And so essentially in a GLM, what you have, so notice that another way to think about a logistic regression model is that you're essentially saying that W transpose X is equal to log of the probability over 1 minus the probability. So essentially there is a special function that is being applied, and the probabilities are, a function of W transpose X. So essentially there is something called a link function. And if I remember correctly, the sigmoid is an example of a link function. I might be butchering this. You should look in a book on generalized linear models. But there is a whole generalization of these to more general functions instead of the sigmoid. That's what I'm trying to say.
Fair enough. If no one's going to ask more questions, I'm just going to hog. That's okay.
Yeah, sure.
I have a super pedantic question that I think I know the answer to already.
Okay.
But on one of the slides, when you were showing the theta t update, I think it was like 2 or 3 from here.
Mm-hmm.
It was a derivation right at the bottom of the slide.
Mm-hmm.
There.
Yeah.
So should that be on the second last line and the rightmost x? Should that be an x transpose?
It does seem very likely it is an X transpose. You mean here, right? Yeah, otherwise the dimensions don't make sense. Thank you. Yeah, I actually just made slides for this course, so I assume there's infinite mistakes scattered around. So thank you.
Just trying to check my understanding here.
Mm-hmm.
Cool. Okay. And is the general story here with logistic regression to try to create a predictive model? Like, let's say we had a data set of dogs and cats, and we hired a bunch of people to do data set labeling. If we ran the algorithm here on the outcome, would we get a function that sort of well characterizes the people we hired to do the labeling?
Yeah, exactly. Yeah. That's, I think, best understood by staring at this curve, right?
Yeah.
Yeah, exactly. Mm-hmm.
Cool. Super clear. Thank you.
Thank you.
Professor, can I ask a question about the assignment?
Yeah, of course.
So for the assignment tool, you want us to use the clamp function, but is there a data given for the value of the clamp function? I mean, the value of the bound?
Are you talking about the second homework?
Yeah, the second homework.
Let me just open the second homework to refresh my memory. Are you talking about task 1, 2, or 3?
Task 1. Yeah, task 1.
Oh, you were saying the clamp. Were you talking about the clamp?
So for the clamp, we need a lambda, right? So do we know the value of lambda, or is it given in the code?
Oh, I see. That's a good question. It should be given in the code. The lambda is the epsilon. I should have mentioned that. That's actually a good point. Let me verify, just 1 second. Let me verify so I don't confuse you.
Wait, but I think the epsilon is a constant in the project gradient descent formula.
Just 1 second, please. 1 second.
Okay.
Let me just verify I'm not confusing you with an incorrect quantity. Let me see. What is this? With the epsilon, you should use the epsilon.
Oh, I should. Okay.
It's alpha that's the clamp, right?
No, it's the epsilon. It's the epsilon.
Oh, sorry. The alpha is analogous to lambda in the thing, right?
Alpha is analogous. Oh, I need to open the lecture slides for that. I don't remember by heart. You're referring to the lecture slides, right?
Yeah.
Yeah.
I see. So it would have made a lot of sense if I actually used the same terminology, wouldn't it? It would make a lot of sense. Yeah, so lambda in the slides is epsilon. 1 second. Let me verify again.
But there's an epsilon in the slides as well.
1 second. I understand this is confusing. It is confusing. Let's see. So the clamping in the slides is with lambda, right?
Yeah.
So I think the clamping should be with alpha.
Okay. Yeah.
Is it possible that my implementation is incorrect of the homework? I feel like one second. Where is my implementation of the homework? I think I might have made a mistake. Give me 1 second to verify. What did I do? Yeah, I think I got them mixed up even in my solution, unfortunately. I think they should be, because alpha is 2/255, right? 2
Yeah.
over 255 is trying to indicate that the alpha is normalized grayscale scale. So the way it works is that images have pixels which have colors, and the grayscale pixels are 8-bit, which
8
means
bit.
that you have 255 possible values, like between 0 and 255. So it's 256 values.
Okay.
So like 2 over 255 indicates, 2 gray levels. Let's see what happens. Does my code produce a reasonable result if I fix it?
I think if you switch, so if you let epsilon equal epsilon in the code, the picture comes out nice. And if you swap them, it comes out grainy. It's like,
Yeah, I think mine was grainy, but let's see. I just fixed it. So you mean if you use the incorrect values, you get a dog which has some type of marks on it? Okay, yeah. Okay. That was a mistake. Wow, you found a bug in my code. So embarrassed. This is the biggest shame. Biggest shame.
wait, did we? I mean, should epsilon be epsilon in the slides?
Okay, so let me look at the slides now. In the slides, epsilon is analogous to epsilon, and alpha is analogous to lambda. What I was referring to is that I have an implementation of the homework, right? I verify that this thing is solvable before I give the homework. I try to solve the homework. And in my solution, I actually got them mixed up, which is why my solution looked kind of strange, actually, now that I think about it. Because my dog had like a bunch of grains on it, as you mentioned. What kind of class do you get, by the way, when you attack the model? Do you know?
What do you mean attack?
So when you create the adversarial example, right, then, so did you solve the homework or you didn't solve it yet? You said that you solved it, right, within 15 minutes. So
Yeah.
after you attack the model, meaning that after you generate the adversarial example and you run the code, you get 2 images of a dog, right?
Yeah.
The dog. So it's like a pug, and above it says pug. And next to it,
oh, I got a paper towel.
oh, you got a paper towel. Okay, I got something different. Huh. I'm wondering if it's supposed to be deterministic or not. Oh, maybe we have a small difference in the implementation or something.
So I'll rerun with the switched things.
Lambda is analogous to alpha and epsilon is analogous to epsilon. That's the correct correspondence to anyone who's watching.
Okay. So that would be paper towel, and I think the other way is mouse.
I'm getting a Pekingese, which I think is a type of a dog. But maybe there is a small difference between the implementations or something.
I mean, I can PM you the operative line if you like.
I think you messaged a different person, or you didn't message me.
I may have messaged your iPad. Oops.
Oh, that's possible. Yes, that is possible. Okay, I see. Let's see. Yes, so my implementation is slightly different. Oh, but that's for the adversarial attack. 1 second. Yeah, I think it looks reasonable. I mean, I cannot say immediately if there's no issues, but it looks like a reasonable implementation. Yeah.
Professor, I actually have some difficulties for the whole in terms of the code. Like there are lots of input in the like formula, and like how do we kill the x? Like how do we kill the input? Like there are input of x and there's input of zeta. Wait, let me just.
Input of x. Are you referring to task number 1 or 2 or 3?
Oh, task number 1, yes.
So let me remind myself what is task number 1. Very short span memory. I already forgot.
Are you trying to isolate your ZK?
Yeah, which so
yeah. I'm trying to create a code for my ZK. ZK plus 1 and the ZK, I guess. So I need to use a loop and
no, you don't need a loop. You don't need a loop.
I don't need a loop?
No.
Oh, okay.
A loop over what? Maybe I should ask.
I mean, you have you mean you have z0 equals 0 and zt plus 1 equal to zt plus
Right, but if you look at the code inside the PGD attack function, do you see how it says for I in range iters? Do you see that line?
Oh wait, okay.
So that line is responsible for iterating the code. So I is analogous to T. I should have perhaps
Oh,
used
I
T.
I see.
The only thing that you need to implement is the equation of zt plus 1 as function of zt, right? That's what you need to implement.
So you are saying that ZT has already been built inside some function?
Yes. So ZT, let's see, what is ZT? I mean, you have at each iteration the adversarial image and the original image, right?
Yeah.
So what is the relation between ZT and those two quantities? The adversarial image minus the original image gives you the current Z, right?
Oh, okay, yeah. The virtual image minus the, okay, wow.
But do you even need ZT actually, now that I wonder? Oh, you do need ZT. You need to do ZT plus the sign, yeah. So essentially you need to implement the ZT plus epsilon multiplied by the sine, the gradient, and so on.
Yeah. Okay, so the ZT here means it is the difference between the logits and the predicted class.
No. So ZT is a perturbation on the input, right? It's a perturbation on the input. So it's the difference between the adversarial image and the original image.
Original image. Oh, I see.
It's
Okay.
it's in the space of the input, not the output, right?
Oh, okay. Yeah. I see.
Would it be?
Oh.
Sorry.
Sorry. Okay. So, but for the hint in the first task that you said, you can access the gradient of the tensor as a adversarial image dot grad, right?
Right.
But after we use that, we should still evaluate that gradient at v equals x plus ct.
So the thing is that there is a line which says loss function logits label backward. Do you see that line?
Yes.
Now, notice that above that line, there is a line which says logits equal to model adversarial image. Do you see that?
Yes, I saw that. It's for forward pass, right?
Right. Notice that the forward pass is being evaluated on the adversarial image.
Yes.
And so because the forward pass is being evaluated on the adversarial image, the backward pass will calculate gradients at the point of the adversarial image.
Oh, I see. So by using the hint you give us, we have already evaluated the gradients at that point.
Exactly. Yeah.
I see. Okay. Oh, yeah. The most thing bugged me in the assignments are the how does the PyTorch work in general?
Yeah. It's highly non-trivial.
Yeah. Okay, thank you, Professor. I will finish this.
No worries.
As soon as possible.
If you have problems, you can email, ask questions.
Sure. Thank you.
Don't waste weeks of your time trying to figure out something that I can assist you with.
Okay, thank you very much. Thank you.
So, do you think it would be a useful use of my time to dig into PyTorch and figure out what this detach does and stuff like this?
I think so. It seems like you're already at a high level. You already have high level PyTorch skills. If it took you 15 minutes to implement this, so I think if you're at that level, it would probably be a good idea to learn, these extra steps. Yeah, detach is one of them, but there's other things that you might want to also learn about, like unsqueeze and squeeze, if those don't make sense, or how part of the code is creating a normalization module and then concatenating that to the ResNet, right? That's another thing.
Right.
I guess it depends, what's your use case. If your goal is to, at the end of the day, if your goal is to try and do something exotic, let's put it that way, in deep learning, then it's very likely you would need this type of deeper understanding of PyTorch. But I'm not sure how does one gain deeper understanding of PyTorch except just looking at codes, right?
Just reading the docs and stuff?
I think reading the docs is a bit robotic. I don't think I've ever learned how to program by reading docs, but there are people who I guess do that, right? My approach would be, first of all, I think the homeworks are showing you at the end of the course, you would see like, a large subset of all the commands I know of PyTorch. So I think that would give you some pool of knowledge. And besides that, I think you can look in PyTorch. There is different tutorials that people do there, that they write there. I think those are extremely useful. I can show you what I'm referring to. So in the main PyTorch website, there's something called tutorials. If you click at the top, and then there is many pages of examples. There is a 60-minute blitz to PyTorch. There's object detection, transfer learning, adversarial examples, GANs, audio, sequence to sequence with transformers, many different things. So I think those are probably the best tutorials that you would find. And they would show you also content beyond what will be covered in this course. For example, I won't be talking about, transformers, or I won't be talking about language models. And if you just look at those tutorials, I think it should be pretty clear.
Cool, thanks.
Yeah, and if you have questions about the tutorials, I would also be, of course, happy to answer. I haven't done all of them, but if you find a tutorial, I would be happy to look at it. Tutorial that doesn't make sense or something.
And just one last thing, do you have a sense of when the problem set, the first problem set's going to come out?
How many problem sets are there going to be? How many did I
4.
say? 4. So I'm probably aiming at quarter of the course. So if we have 12 weeks, a quarter of the course is actually now. Okay, so it should, I guess, now that you mentioned, it would probably be very soon.